Hello everybody, and welcome to our last video on the ruler function. In this video, we'll be talking about part G of the ruler function problem that started on page 61 of the workbook. This particular part of the problem you'll find on the top of page 62 in the workbook. Again, what we're trying to convince ourselves of with these problems is a conjecture about the ruler function. Despite its unusual bouncy behavior, we're trying to convince ourselves that we get a limit of 0 for this function. The basic reason for that is that there are a lot of points that we haven't plotted on this function that are close to 0. Some rational numbers down here, and then irrational numbers right along the x-axis. And g gives us a particular value that we'd like to be concerned with, so in particular we're starting with x not equals 1/4 again. And we're going to try to find a number, delta 4 greater than 0, so that if x is close to 1/4, okay, in other words, within delta 4, whatever that number turns out to be, we're going to try to convince ourselves that we can make the output value f of x within 1/5 of 0. So like in the example that we did in the last video, this 1/5 here creates an epsilon neighborhood that we'd like to be in. Okay, let's draw that epsilon neighborhood into our picture. So 1/5 would be right here along the dotted line. Let's draw that in, and then negative 1/5 is down here. And so we're trying to create a neighborhood around 1/4 so that if we plug in any x value in that neighborhood, excluding the point right at the center, the 1/4, that all of our y values lie in that epsilon zone that we just created between here and here. Okay, and we'll use the same strategy that we used in the last video. To guarantee that all of our points are in that epsilon zone, we'll think about the points that we need to avoid, the ones that are not going to work, that are going to be outside of that zone. Okay, so we'll do what we did last time and start by circling some of the points that we need to avoid. Okay, 0 and 1 again are well outside of our neighborhood, so those are first on our list of what we need to avoid. Okay, and 1/2, that's certainly outside of our zone. 1/3 and 2/3. Okay, 1/4 and 3/4. All of those points we wanted to avoid in part, the previous part of the problem as well, but there are some new points that we also need to avoid. Oh, and actually, I apologize, I misspoke. We just talked about how we really don't need to avoid 1/4 because that's our starting point. Okay, again, this condition here guarantees that we're not considering x not equal to, or x equal to 1/4. Okay, so we don't need to avoid that one, but we do need to avoid these points that are right on the edge, okay, of our epsilon zone, and so they're not contained in it. So this list is a little bit longer than it was last time. Let's go ahead and complete it. So we're going to avoid 1/2, 1/3 and 2/3, 3/4, and then 1/5, 2/5, 3/5, and 4/5. Let me just briefly check and make sure that that list is correct here. Okay, looks like we're good. And the question is, how big can we make our number delta 4 so that we don't capture any of those points that we don't want? Let's do what we did in the last example and first choose a neighborhood that's too big. Okay, again, what if we chose something like 1/4? Okay, so a delta that would be that big. Okay, well, our delta neighborhood then would include all x values that are between those lines, essentially. And notice that we capture some points that we don't want. Okay, I see 3 of them. So there, there, and there. All of those points are between the blue lines and they're outside of the epsilon zone. So this delta is too big because it captures some points that are outside of our epsilon neighborhood. We need to go smaller so that we eliminate all of those points. Okay, so let's erase this like we did last time. And this delta is going to need to be really small because we're going to need to avoid this point right here that's relatively close to our starting point of 1/4. Okay, and in fact, I claim we'd have to make it really small, maybe like that on our picture. I'm going to go ahead and draw in the blue lines here. Okay, notice that if we make delta that small, then that problem point that's sitting right here is right on the line, which doesn't count. It's not in the delta neighborhood between those two blue dotted lines. And so this delta, whatever it is, should be small enough. All of the other points that we can't see are either going to be down here, if they're rational numbers, or if they're irrational numbers here. Okay, and the last question is, how big is that delta? Well, that would be the distance either from here to here, or we could also measure it on the other side because this neighborhood is symmetric. So we can measure that distance by figuring out what this point right here is. And we know from our previous work, kind of engaging with this grid, that that number is 1/5. Okay, so our delta looks to be the difference then between 1/4 and 1/5, and we can go down here and calculate that. Okay, and again, I'll leave the fractional arithmetic to you. You can do this calculation and confirm that you're going to get 1/20 out of that. So in a nutshell, what we've proven is if we choose delta 4 equal to 1/20, then any x value that satisfies this statement right here, okay, visually that's going to be between the two blue dotted lines, is going to also satisfy this statement. All of the output values are going to be between -1/5 and 1/5. And the idea is if we were to continue this and take numbers smaller than 1/5, maybe 1/6 or 1/7 or 1/8, we can go as small as we want to. It will always be possible to choose a delta small enough to avoid the finitely many points that don't work, that are outside of our neighborhood, and therefore what we ultimately reach is the conclusion that this statement is plausible, that the limit of this function really is 0. And if you want to see the proof of that, you can look at Part H on page 62 of the workbook from the notes.